802.11 Network Architecture, part number 1. In this video, we'll learn about how wireless LANs are organized, and we'll learn about the terms that are used to define how a wireless LAN is organized. And we'll also learn about the process that a wireless client, which is also referred to as a station, we'll learn about the process that a station goes through in order to find a wireless LAN. Wireless LAN isn't very much good to us if we can't find it and then, as a result, connect to it. However, we might have more than one access point in our wireless LAN. So we'll also learn about the process that is involved for roaming from one wireless access point to another wireless access point in this video. So align your antennas into receive mode because we're going to get started here. And let's answer that age-old question, how are wireless LANs organized? And to answer that question, we're going to bring up a whiteboard. And the basic answer to that question is that wireless LANs are organized in service sets, and a service set is really just the key components of a fully operational wireless LAN, and there are 3 different types of service sets that we can create to establish a wireless LAN. We can have a basic service set, an extended, or an independent service set. So let's learn about each of these service sets, first starting with basic, and to learn about a basic service set, let's bring up another whiteboard here. The essential ingredients of a basic service set is that you have only one access point connected to your wired network and have one or more wireless stations. And this is also referred to as infrastructure mode. Infrastructure mode requires that an access point be used in order to transmit data wirelessly. So meaning that there's no direct client-to-client communication for transmitting the data wirelessly. All the data that's being transmitted goes to and from the access point. So if I need to transmit data from this laptop over to this laptop, that data is going to go to the wireless access point and in turn back out this way. So the wireless access point is kind of like a hub in this context here. Everything goes to and from the wireless access point, and this is a basic service set operating in infrastructure mode. Now, the circle that we see here surrounding the basic service set, or the BSS, is referred to as the coverage area, which is technically called either a single cell or an RF area. It's the area in which a wireless client can establish a wireless connection to the wireless access point. Now, the closer the client gets to the wireless access point, the stronger connection they'll have, and as a result, they'll have a faster data rate. However, the further away the wireless client gets, meaning as they get closer and closer to the edges of this circle, the edges of the RF coverage area, then it's a weaker connection, and as a result, the data rate speeds are reduced. So again, a BSS consists of only one wireless access point, and that wireless access point must be running in infrastructure mode, meaning it's not running in repeater mode, it's not running as a bridge, it's running in infrastructure mode, or basically it's behaving as a wireless access point, and each wireless client must use the access point in order to transfer data with any other wireless clients or wired clients, for that fact, that the wireless access point is connected to. Also, the BSS only has one unique SSID. We learned about an SSID in a previous video, but a little refresher. An SSID is the name of the basic service set, or the name of your wireless network. SSID stands for Service Set Identifier. So that's service set number 1, a basic service set. Service set number 2 is an extended service set. Let's bring up another whiteboard and learn about this service set. Now, the essential definition of an extended service set, or an ESS, is that it contains 2 or more basic service sets that are connected to a common distribution system, such as our wired network here. So both access points, or both BSSs, are connected to the same wired network. Also, an ESS must have at least 2 wireless access points operating in infrastructure mode. So again, they're not operating as a repeater, they're not operating as a bridge, they're operating in infrastructure mode, which again allows the wireless clients to be able to use either one of these access points, depending on obviously the one they're connected to transmit data wirelessly to and from other clients on the wired or wireless network. And as you see here, the ESS contains 2 or more cells or 2 or more RF coverage areas which may or may not overlap. If they overlap, that helps to facilitate roaming of a wireless station from one BSS to another BSS and vice versa. And another thing to take note of is that the BSSs that comprise the extended service set can have a independent SSID, meaning the name of this BSS could be, let's say, for example, Lab 1, so that's its SSID, and the SSID of this could be, let's say, for example, Sales. So they could be the same, or they can be different, or they can have unique SSIDs. So that's service set number 2. Let's take a look at our last service set, which is an Independent Basic Service Set, or IBSS. Now, an IBSS is also referred to as an ad hoc network. And in an IBSS, or an ad hoc network, as you see here, there is no wireless access point. This is essentially a peer-to-peer network where each client has its own wireless network adapter, and as a result is acting as both a client and a wireless access point. So it's both sending and receiving. So again, because the stations within an IBSS are not connected to a wireless access point, it is the responsibility of the station to transmit the data wirelessly from one station to another. So for example, if this laptop is configured with a wireless network adapter, and this laptop is configured with a wireless network adapter, this laptop can send data wirelessly to this laptop, so essentially we have a peer-to-peer environment here, and vice versa. So we have a coverage area here as well. Each of the wireless network adapters have a radio that can transmit and receive data within a specific coverage area. So we have a single cell within IBSS. Also, all the stations that want to partake in this IBSS must have the same SSID. So an IBSS has to have one unique SSID. So the process of creating an IBSS is very similar to creating a workgroup environment with Microsoft Windows operating systems, where if you want to be able to browse the network for computers within your peer-to-peer workgroup, each computer in that workgroup must have the same workgroup name. So those are the 3 options that we have available for organizing a wireless LAN, but you might be asking yourself now, well, how in the world does a wireless station find a wireless LAN to begin with? Well, to answer that question, let's bring up another whiteboard. Now, in order for a wireless station to be able to find a wireless LAN, it's going to listen for information that a wireless access point broadcasts out about its capabilities. One of the things it's going to listen for is the service set identifier, or the SSID. And again, the service set identifier is the name of the wireless LAN. And the service set identifier can be 2 to 32 characters. There can be alphanumeric characters, meaning letters and numbers. And the SSID is case sensitive. So if you have one of the characters as uppercase, you have to type that in as uppercase on the wireless station. Now, this process of listening that is done by the wireless station is referred to as scanning. And as a default, the radios in the wireless network adapters on a station will passively scan all the radio frequency channels and listen for the broadcasting of a service set identifier and a beacon frame. Now, a frame is a packet of information that's transmitted wirelessly between the wireless access point and the wireless station. And there are 3 main types of frames. There are control frames, data frames, and management frames. And a beacon frame is a type of management frame. And a beacon frame is really the heartbeat of a wireless LAN. It's a pulse that is sent out by a wireless access point that provides stations with a lot of information about the wireless LAN. So, for example, a station will passively scan for these beacon frames which are broadcasted by a wireless access point. And these beacon frames contain capability information and general information about the wireless access point that is broadcasting this heartbeat of the wireless LAN. It's saying, hey, this is me, this is the wireless LAN, this is what it consists of, and this is what it's capable of. So, for example, the service set identifier, the name of the wireless LAN, is actually tucked inside a beacon frame. Let's bring up another whiteboard and take a look at some of the other contents of a beacon frame. Now, a beacon will contain a timestamp value, which is the time of the local clock on the wireless access point. And what happens is the wireless stations that connect to a wireless access point will use the value in this timestamp that is transmitted again in a beacon frame by the wireless access point to update its local clock. So by doing this, this ensures that the clock on the wireless access point and the clock on the wireless station are in sync. And as I mentioned just a moment ago, the SSID will also be transmitted within a beacon frame. Now I state here that it may be displayed within the beacon frame. And I state that because wireless access points give you the capability of disabling or enabling the broadcast of the SSID. So if the broadcasting of the SSID is enabled, you'll see that name within the beacon frame. However, if the broadcasting of the SSID is not enabled, in replace of the name, you'll just see the value of null. It'll just say NULL, null. And let's bring up another whiteboard and learn about some other key values that are contained within a beacon frame. So another content that you'll find within a beacon frame is the supported rates of the wireless access point. So for example, this will be the data transfer rates that are supported. So for example, if it was a wireless access point that uses the 802.11.b protocol, it would support the data transfer rates of 1, 2, 5.5, and 11 megabits per second. The contents will also contain what's called parameter sets, and the parameter sets indicate the spread spectrum technology that's being used by the wireless access point, meaning is it using FHSS or DSSS. And a beacon frame will also contain information for wireless stations that are in power saving mode. This is called a traffic indication map, or TIM for short. So for laptops, for example, that are using the battery and they're in a temporary sleep mode, what will happen is the wireless access point can store or buffer data on the wireless access point until the wireless station comes out of sleep mode and actually can receive the data that's been buffered. And we'll learn more about that in the next video, Network Architecture Part 2. So those are the key contents of a beacon frame, and you can view these beacon frames by using what is referred to as a wireless protocol analyzer, or what is generically referred to as a sniffer. And let me bring up a website that contains a table of wireless sniffers, both for the Windows and Linux platforms. So a popular sniffer is called AirMagnet for the Windows platform. Another popular sniffer is called AeroPeak for the Windows platform. And for you Linux gearheads, there are sniffers for Linux as well. So one of the things that I really stress, though, before you go out and get a Wi-Fi protocol analyzer or a sniffer is to ensure that the software is compatible with your wireless network adapter. And that is harder than it sounds. Because what happens is your wireless network adapter as a default is not able to capture packets in what is referred to as promiscuous mode. As a default, a wireless network adapter will only capture packets that are sent between the adapter that is installed in your station, for example, your laptop. It's going to capture packets between the laptop and the wireless access point that is transmitting to and from. While in promiscuous mode, it's going to capture all the packets that are within the transmitting area. So it's going to capture packets from other wireless access points, other stations. So as a default, again, the wireless network adapter does not capture packets in promiscuous mode. So these sniffers will install a special type of driver to allow it to operate in promiscuous mode. And that's where things can get into the rub, because there's very few wireless network adapters and their associated original equipment manufacturer drivers, or OEM drivers, which will work well and in tandem with these special drivers to allow the network adapter to capture these packets in promiscuous mode. So spend your time, do your homework, ensure that the wireless network adapter that you're using within your company is compatible with the software that you potentially want to purchase for sniffing out these beacon frames. Now, what I have done in this example is that I have found a sniffer that is compatible with the wireless network adapter that I have. It's called Observer. It's down here. Let me bring it up right now. Now, I found this program, Observer, to be a pretty good program. Let me just show you a little more information about it. It's by a company called Network Instruments, and you can download an eval version from their website, networkinstruments.com. Now, on the right-hand side, we see a window that's been broken into 3 panes. And on the very top pane, we see a frame that was broadcasted by this wireless access point at this MAC address. So in the middle window here, we see the information or the details of this frame. We see that this frame is a beacon frame. And again, remember that I said a beacon frame is a type of management frame. And if we scroll down, though, we can look at the contents of the beacon frame. So we see the beacon frame right here and the contents such as the timestamp, such as the beacon interval, and I'll talk more about that in our next video, the part 2 of network architecture. See some of the capability information. The capability information can indicate that, for example, all the wireless stations must use a WEP for encryption or WPA for encryption. And if we scroll down here, we'll see some of the other contents that we talked about. So we learned that the SSID is contained within a beacon frame, but in this example, we don't see the name of the SSID. It says null, and that's because the wireless access point is configured to disable the broadcasting of the SSID. We see the supported rates of the wireless access point. So in this example, the wireless access point supports data transfer rates all the way up to 54 megabits. And some more information here. So the DS parameter set, so this is what we talked about before. Is it using DSSS technology or FHSS technology? In this example, it's using DSSS, and it's transmitting on channel 7. And below that, we see the traffic indication map, or TIM for short, which again is an indicator of the wireless stations that are sleeping, that have data packets that are queued up or buffered on the wireless access point. So again, we're looking at one packet. This is packet number 2 out of 65 packets that have been sniffed out of the air by this particular program, and this particular packet is a beacon frame. And again, a beacon frame is a type of management frame. So again, as a default, wireless stations will passively scan for these beacons. However, there's 2 types of scanning. There's passive scanning and there's active scanning. Let's learn a little more about scanning by closing out of here, going to our whiteboard here. So we've learned that passive scanning is the process for listening to these beacons on each channel. So again, this passive scanning of the beacons that are transmitted by a wireless access point allows a wireless station to assess the capabilities of a wireless access point. And this becomes very important when there are multiple wireless access points within the RF range of the station that wants to join a wireless LAN. So it can assess the signal strength by, again, getting the information from the beacon. Let's say, for example, there's 2 wireless access points that are within the range of the laptop computer that wants to join a wireless LAN. Well, it's going to look at the beacons that are transmitted by both of these wireless access points, and all else being equal, it will attempt to join the wireless access point that has the strongest signal strength and the lowest bitrate error rate. So essentially what's happening here is that the wireless station is lurking in the background, listening for these beacons that are transmitted wirelessly, but what it's listening for is a beacon that is transmitting the same SSID as that is configured with. So for example, if a laptop with a wireless NIC is configured with the SSID of Nugget Lab, it's going to listen to wireless access points that are also transmitting the name of the SSID Nugget Lab as well. So if there's 2 wireless access points that are transmitting the SSID of Nugget Lab, the station is going to assess the capabilities of these 2 wireless access points by looking at its signal strength and the lowest bit error rate. And by using that information, it will then attempt to join the wireless LAN by going through the wireless access point that has the strongest signal rate. Now, the fun doesn't stop there. A station, once it has associated and it has authenticated and connected to the wireless LAN through a wireless access point, will continue this passive scanning. And it does that for 2 reasons. Number 1, it does that so in case its connection gets dropped, it can reconnect very quickly. And number 2, it does this for roaming purpose. Now, we'll learn about the roaming in just a minute here, but Once the wireless station has connected to a wireless access point, we'll learn about that method of associating and authenticating in part 2 of this video. But once it's established that connection, or what's referred to as an association, it continues the passive scanning to save time in case the connection gets dropped. So if it knows about the signal strength of a wireless access point and it knows that it's there, it saves time reconnecting to the wireless network in case it was disconnected from a wireless access point. So it says, hey, here's a wireless access point at this MAC address. I know its signal strength, and my connection got dropped for whatever reason. I'm going to try to reconnect to that access point at this MAC address, and hopefully I'll get reconnected. So through the process of passive scanning, a wireless station will build a list and maintain a list of the wireless access points that are broadcasting these beacon frames, and by doing that, this list will help the wireless access point to determine which is the best wireless access point it should connect to in case its connection is dropped. So it'll maintain a list of the wireless access point's characteristics and capabilities, such as the channel it's broadcasting on, its signal strength, its SSID, etc. Now, in addition to lurking in the background and passively listening for beacon frames that are transmitted by the wireless access point, the station can do a little role reversal. The station can be an active participant in the scanning process by sending frames. So, for example, if the wireless station is actively seeking to connect to a wireless access point, meaning that they want to connect to a wireless LAN, so when the wireless station first starts up, it's going to actively seek a wireless access point, or if a user simply clicks on a connect button, so I want to connect to a wireless access point right now, in those situations what will happen is the scanning process flips, if you will. It goes from the passive mode to an active mode, and the station will send out what's referred to as a probe request frame. And the frame, this probe request frame, will contain the name of the SSID, or the name of the wireless network that it wants to connect to. So, for example, if a wireless station wants to connect to a wireless LAN named Nugget Lab, it's basically going to broadcast out a probe request frame saying, hey, are there any wireless access points out here at all with the name Nugget Lab? And if there are any wireless access points, they're going to, within range of this broadcast, they will return what's referred to as a probe response frame. And the probe response frame will contain the name of the SSID, which in this example will be Nugget Lab, and it'll also contain the capability information of that wireless access point, so the station can assess, if there's multiple wireless access points with the same SSID, which is the best wireless access point to connect to. So it's saying, hey, anybody out here with the name Nugget Lab? Somebody yells up, yeah, I'm here. Another person says, yeah, I'm here. Another access point says, I'm out here. The station says, whoa, okay, hang on a second. Let me know who has the best signal strength. Okay, you do? The one at this MAC address? Cool, I'm going to attempt to connect to you right now. Now, the scanning process is also used when wireless clients are roaming. Let's bring up another whiteboard and learn about roaming. Roaming essentially means that a wireless station can move from one cell coverage area to another coverage area without any break in their connectivity. So in this example here, where we have two wireless access points, we have Station 1 and Station 2, these two laptops here that are currently associated with this wireless access point. Well, if the person at this laptop here picks up their laptop and maybe goes down the hall to a meeting room or a boardroom, they might associate with another access point. As the signal strength here gets weaker and weaker and the signal strength here gets stronger and stronger, the passive scanning that the station does in maintaining the list of access points with the higher signal strength, it's always going on. It's going on in the background. So as the station moves closer and closer to this cell area of this BSS, the signal strength will get higher and higher, and the beacons that are transmitted from this wireless access point right here will indicate that the signal strength is getting higher and higher. So typically, to facilitate seamless roaming, there should be about a 20 to a 30% overlap between the cell coverage areas. So while this client is moving, walking down the hallway, walking down the hallway, walking down the hallway, it will then disassociate from this access point and associate with this access point, but it's all invisible to the user. It's all transparent. Everything just happens in the background, and they maintain their connectivity as they're walking from their office, down the hallway, down to the boardroom for their meeting, and they could be surfing the web while they're walking, and they're connected through the whole process. So again, in order to allow seamless roaming, where the client always maintains connectivity as they're being disconnected from one access point and connected to another access point, there has to be overlap between the coverage area. If there's no overlap, and the user walks down the hallway and all of a sudden gets in this dead zone, if you will, where there's no wireless coverage, then their connectivity will drop at that point. So in order to maintain the seamless roaming, you need to provide a 20 to 30% overlap, but something you got to watch out for is that in order to provide this overlap, you want to ensure that the channels that the wireless access points are on non-overlapping channels. So for example, you might want to have one access point on channel 1 and another one on channel 6. If they are on overlapping channels, interference will come into play, and as a result, you'll have less throughput, especially within the zone where there's overlapping between the RF coverage areas. So again, because the clients are always passively scanning for beacons transmitted by a wireless access point and maintaining tables of the wireless access point's capabilities, this helps to reduce the time it takes for clients to be able to find and associate with wireless access points while they're roaming as well. And with that, that brings us to the end of this video. Let's bring up our whiteboard and do a quick recap of what we've learned here. So we started this video off by learning that wireless LANs are organized in service sets, and there are 3 different types of service sets. There's a BSS, which has how many access points? Anybody? That's right, 1 access point, and it has 1 unique SSID. In contrast, we can have an extended service set, or an ESS, which has 2 or more access points. However, they can have different unique SSIDs. So if we have let's say, for example, 3 wireless access points in an ESS. Each one of those access points can have a unique SSID. And lastly, we can have an RF coverage area without any access points at all by using an independent basic service set, or was also referred to as an ad hoc or a peer-to-peer wireless coverage area. And we also learned that wireless stations will use either passive scanning or active scanning for locating a wireless LAN. In passive scanning, it listens to beacons that are transmitted by a wireless access point. In active scanning, the wireless station will transmit probe request frames to a wireless access point, and the wireless access point will respond back with a probe response frame. And we learned that in order to provide seamless roaming capability for a wireless station to maintain connectivity as the station is moving from one access point to another access point, you need to have a 20 to 30% overlap between the RF coverage areas of the access points, and also ensure that the channels that are used by the wireless access points do not overlap. And with that, that brings us to the end. I hope that this video has been informative for you, and I'd like to thank you for viewing.